So if you're curious where this actually comes from, we talked about the multiplication rule. You remember the multiplication rule has conditional probabilities within it. And if you just manipulate the multiplication rule a little bit, like push symbols around a little bit, you'll see that it equals this. And try it on your own, and if you're curious as to where this comes from, you can see me and we can derive it together. But for now, this base theorem just comes from the multiplication rule. And so if you apply this onto our example, in our example, we were trying to find this particular conditional probability, which is the probability that you have HIV given that you test positive. So basically, having HIV would be event A in this base theorem, and testing positive would be event B, because it matches this template. And so let's expand this out in words first. So the first part of base theorem is the probability of B given A, so what would that be in words? Probability of what given what? Yeah, probability of, so B is testing positive and A is having HIV, so this will be the probability of testing positive given HIV times the probability of A. What would that be in our example? Sure. Yeah, that would be having HIV, the probability of HIV, divide by probability of B. Yeah, testing positive. So let's go ahead and substitute in the numbers for these probabilities. So this first probability, the probability of testing positive given that we have HIV, what number would go there? Yeah, that's directly given in our situation. That would be the 0.9999. And then this probability of having HIV, where would that number go?
Are we doing 110 or 1?
Yeah, let's do the new one. Let's do 110. So that would be 1/10 or 0.1. And then what would this probability of testing positive be? How do you get that?
Would you have to use the addition rule?
Yeah, okay, very good. So you might recognize then that the facts that we're given here, we can't use these directly in finding the probability of testing positive. Because here, we know the probability of testing positive, but this is only under the condition that somebody already has HIV. Then it'll be this number. But we don't have the probability of testing positive, period, in the three facts that we're given. So at this point, you would be stuck if you were relying on the formula. But if you had built a table, then could you find this probability of testing positive?
Yes.
Yeah, how would you find it?
Adding the positive column and dividing by the sample.
Very good. So you would just add this row total representing testing positive, and you would divide by the total number of people, which I erased it, but it was 100,000 in this case. So again, the population size was 100,000 that we used. So you would add these up and then divide by 100,000, and that would give you exactly the probability of testing positive. But that's if you had built this table, then you would know what to plug in the formula. But then you might ask, well, why would we use the formula in the first place if we're going to build a table? If we built a table, we could just go ahead and find this conditional probability we wanted immediately, without having to use the formula. And that's a valid point. And that's why I'm showing you both. Is that if you were to start with the formula and you were to get stuck, you might have to build a table in order to get some pieces of that formula. Any questions? Okay, and so because of this, also there are different variations of this formula. It turns out that this this part here, the probability of B, actually expands out into something, and it expands out into this. All right, so this one probability of B actually expands out into this entire expression, which is the probability of B given A times the probability of A. So this first part here, you notice it's actually exactly the same as this numerator. And then plus this second term here, which is the probability of B given not A times the probability of not A. So this is a variation of Bayes' theorem. You can think of it as the expanded version. If you start with the first version and you're stuck or you don't have enough information, you can try the expanded version. So let's go ahead and try the expanded version. So if we use the expanded version here, again, we have a sum between two things, and the first term here is the same as the entire top one. So we're going to go ahead and just copy that down. But now we're going to add in this part. So this would be the probability of B given not A. What would that be in words in our problem?
Probability of being positive given that you don't have HIV.
Yeah, so just match the template here. So B is positive and A is HIV, so the probability of B given not A would be the probability of testing positive given that you don't have HIV. So positive given not HIV times the probability of not A, which is not HIV. All right, so let's go ahead and substitute in numbers here into this expanded version of the formula. And by the way, on a test or any testing situation, you would not have to memorize this formula. You'll have access to this formula. So this looks pretty hideous, so don't worry about having to memorize this. All right, so let's go ahead and plug this in. So the first part in the denominator here, again, is exactly the same as the entire numerator. So we can just replace those numbers. And then what about the second part of this denominator here? So let's first come up with the probability of testing positive given that we don't have HIV. So if we look at our facts here, how can we determine that? So we want a positive given that we don't have HIV. In other words, everybody who doesn't have HIV, what fraction of those test positive? So you notice that of these two probabilities, there's no one that looks exactly like that. Yeah.
Would be 0.0001.
Not quite, but close though. So of these two probabilities, there's none that look exactly like the one we're trying to find, which is the probability of testing positive, given that we don't have HIV.
So what do we just do, 1 minus 0.9999?
Close, but not quite, so let's talk about it.
The positive,
Yeah, so this is saying that out of everybody who doesn't have HIV, so now you're gonna look at the probability that has that condition of not having HIV. So that's this one over here, not this one. So it's this one here of not having HIV. So of that group who doesn't have HIV, the percentage who tests negative of that group is 99%. So what would the percentage of testing positive of the same group be?
1%.
Yeah, it would be the complement of this. So it would be 1 minus 0.99, which is 0.01. So this probability here of testing positive, given we don't have HIV, is going to be 0.01. So what about this probability of not having HIV?
0.9.
Yeah, because the probability of having HIV out of everybody is 1 in 10, so not having HIV will be 9 in 10, or 90%. Okay, so now that we have all the numbers in our formula, just go ahead and punch this in, and we'll see what the answer is. And we expect an answer that's the same as the one we got before using the formula from the table. So I'll rewrite this whole expression. So what are you guys doing? Ninety-one point 74%. So you notice that it's exactly the same answer that we got before, by using the table, without using the formula. All right, so the point of all of this is that if you're trying to find a conditional probability, which we said that most interesting probabilities will be conditional probabilities, then there's one of two ways that you can do it. Either you can build a table using those probabilities that are given, or you can use this formula. And the formula has a simplified version, and you should start there, and if you have enough information for the simplified version of the formula, then great. Otherwise, you might have to use the expanded form of the formula, where the denominator expands into this expression. And if you plug in all the right numbers, then you'll get the same answer that you would by building a table. Any questions? Okay. So now that we talk about what Bayes' theorem is, it's used to find conditional probabilities. Let's do some more examples.